and then we're going to get into it. So if you haven't already, please start with your warm-up. It's just 2 questions. Then we're going to go into our presentation. Just so you know, this activity 1 is where you get your worksheet for the lossless compression that we're going to be doing. Activity 2 is a discussion based on the lossy compression. I'll come back to this. Also, we do need to get our AP accounts made. So I hate to say, this is a link to a PDF. This is not the link to the account. But basically, if you put in ap.org, it's going to drop you into this page. You just need to put in your username, which is going to be your MCPS email, your password, and then my code. Where is my fabulous code? Right down here, 2AWD44. Only 80 people have signed up. We need about 120. So please do sign up for your AP account. Think about whether you want to take the test. The test won't hurt you. Apparently the test does cost money to take. It costs $95, I think. So think about that. All right. Back to, oh, there's somebody. Just what I was hoping for. Okay, so Audrey, there's a warm-up to start with right here. Sign up for your AP account if you haven't. And there's going to be a worksheet in this lossless compression, and there's going to be a discussion here in the lossy that we need to do. Okay.
Thank you.
Absolutely. For the warm-up, since most people have had time to do it, let's just share this out. If somebody sends you a message on, off, on, what does it mean? Do you have a secret admirer that's in the computer club? You get a message on, off, on. What does that mean to you? Anyone can answer, just sing out. Come on, you know what you're thinking. You're thinking the right thought, and it's going through your mind. So someone say it. Edward, what does it mean when you get a message on, off, on?
It doesn't necessarily mean anything in particular, but it could mean something.
You have no idea what the heck that means. Somebody sent you some weird spam, is all you know. What you need to, if someone is trying to send you a coded message, you need a key to the code. You need to know what on and off and on represent, if it's something other than on, off, or on. So what we've been working with in terms of coding and sending things is the idea that you need a key. You need to know what those icons represent. Does on mean blue? Does on mean turn on? Does on mean turn off? It could mean all of those things depending on the key. Okay, so let's get into it. Today's presentation. I'm not gonna, the second question is just an ASCII number. It's asking you to create 70 in binary. And my trick for that is to use my beautiful flippy-do. Remember the ones, you get the one number, so you add it up. So it's looking to me like 70 is 1 0 0 0 1 0 0. All right, let's present, and I'm going to have to double tap my fabulous sharing so that I present the right thing. There we are. Oh, yay, look, there's Ethan. Okay. Ethan, if you just got in, we have a warm-up in the modules, and then we're going to do a presentation on lossless compression and a presentation on lossy compression. So if lossless means you're losing nothing, what does lossy compression mean? Can somebody wager a guess?
You're losing a lot.
You're losing, let's leave it at you're losing something. In lossless compression, you're losing absolutely nothing from the message that you're sending. In lossy compression, you might not be able to see or hear the difference in the file, but you have lost some data. You've lost some content from that. So today, what is due is our warm-up, our worksheet on lossless compression, and our discussion on lossy compression. This is not due today. It'll be due at end of day tomorrow because we're accommodating both sections. So that's good for you. You will be able, by the end of today, you'll be able to create a lossless compression scheme and simulate lossy compression using a code.org widget. Okay, I'm throwing people over there. Let me get my breakout rooms too before I lose them. Okay, so just to review, last week we talked about coding a black and white image using 0 for black and 1 for white, using 1 bit. Then we went into coding color images for combining different numbers of bits associated with the colors red, green, and blue in that order. Remember, it is always going red on the outside, green on the inside, and blue. Blue will always be the first numbers of your binary number. Then it goes to green, then red. So with 1 bit, we had a 3-digit binary number. 1 bit for blue, the first one. The second bit was for green. The third was for red. In a 6-bit binary number, or 6-bit system of color, you have 2 bits for blue, 2 bits for green, 2 bits for red. 9-bit system. Now we have a 9-digit binary number, which is very weird because we haven't seen anything over an 8-digit binary number. Same thing, 3 bits for blue, 3 bits for green, 3 bits for red. What that means is I can make 8 different combinations of pure blue, pure green, or pure red. But I can also add a little green into my blue. I can add a little red into my blue, and those are going to make different shades. That's how you modify these things outside of just the true natural color. That you have 8 colors of true green, 8 colors of true red, and 8 colors of true blue. But once you start combining a little green in your blue, it will still look blue, but it will just have a little, red or green in there. Today, let's look at how all the bits can be sent over the internet, which only has electrical signal on and off as a way to send a message. Okay, so what we're going to need you to do is we are going to go to code.org, open up your code.org, and we're going to go Unit 1, Lesson 9, the lesson after the color pixel widget. Lossless compression. This list represents several common abbreviations used in text messages. What other abbreviations could you add to this list? Now I need you, we're going to do this in the chat. So add your favorite text abbreviations and what they mean, because people like me don't really know all the time. I didn't know what the TY was thank you. So BRB, we're not sure what it means. Oh, shaking my head. IMAO, GL for good luck. IDK is I don't know, I'm guessing. NT, nice try. Okay. Why is texting the place for all these incredible abbreviations? Why do people like abbreviations to use when texting? Someone can just answer.
It's faster to write.
Because what?
It's fast, like it's quicker.
It's faster, exactly. Your little thumbs are getting worn out hitting every character. So if you can skip some of those characters and still get your message across, you're doing great. And that's what we're going to work on today. So why might we use abbreviations when sending messages? because it makes our life easier. We don't have to do as much work. And this is the basis of how technologies are made. So what are the advantages? My thumbs don't have to type so many characters, and my friend knows what I'm talking about. Okay, so was everyone able to get your text compression worksheet out of that lossless compression first activity? If not, you can go in the presentation and get it here. Text compression. I want to send this message to a friend, but their phone can only accept 80 characters of text at a time. So the message is, pitter patter, listen to the rain. Pitter patter on the window pane. I notice this pattern has some repetitions in it. So rather than sending the whole message, I send this instead. Okay, so she's sending what's on the right. Star listen _2 sunshine rain star on, it's not star, sun window pane. And that doesn't make any sense to me. But what's this down here? Can someone sing out? What is this area down here?
It's a key.
It's a key. It's a key to our code. We have been sent a coded message by our friend, and this is how to break it down. So what's interesting with this is they have actually broken down words into separate parts, which is very good for a compression scheme. So sun is space, the space. Every time we see sun, it's to the rain. Listen to the rain. On the window. So then umbrella is TTER, but I don't even see any umbrellas. Then snowman is P umbrella. And what I'm calling like headlight is pa umbrella. What the heck is umbrella? It's not even in our message. Oh, there it is, up at the top. Umbrella is TTER. Hang on, I'm not supposed to be going back to it. So P umbrella is pitter and pa umbrella is patter. So they've double nested these things to make this all work. How is this message on the right same as the first on the left? What actually gets sent to my friend? So let me call someone. Kyle 2, how are these messages similar? How are they the same?
What was the other message?
They're both of them are right here. It's pitter patter,
Oh,
listen
okay.
to the rain, and this message in theory is the same thing. How are they the same?
They say the same things.
But one is coded. One is coded with this special key. That's exactly right. What actually gets sent to my friend? What do they receive on their phone? Well, I guess it's two questions. What gets sent to my friend is one question. What do you think gets sent? Kaylin.
Sorry, can you repeat?
What gets sent to the phone? It's sort of a trick question. So saying, what actually gets sent to my friend?
Just the
This
translation.
message or this message?
I mean, the translation does get sent. It's just
Right. All that's going to show up on your phone is this, the translation. Can you see my pointer?
Mhm.
I'm trying to indicate the left. So your phone is going to receive pitter patter, listen to the rain, etc. But this message is also going to be sent to your phone. This is my phone talking to your phone, and your phone is going to interpret this code and present our lossless message. The exact same message I wrote is going to be sent. No information is going to be lost. So using abbreviations and symbols is a form of compression where we try to represent the same information with fewer characters. So, but the new message and key, also called a dictionary, so the original message had 93 characters, but the new message and key, also called a dictionary, have a total of 56 characters. We're essentially sending the same information, but with fewer characters. Our goal today will be to create our own text compression using similar methods. Okay, we're gonna watch this video and then we're gonna jump into this. This is a good one.
My name is Aloe Black. I'm a singer, songwriter, and entertainer. When it became more and more important for artists to have a presence on the internet, I quickly developed the skill to build a website and get online, use my knowledge of coding to make it so that people could learn more about our music. Every bit of data or information can be stored digitally. Whether it's numbers, text, pictures, music, or video, all of it can be represented digitally. That means the information can be represented by electrical signals that are on or off, or as ones and zeros, so to speak. But representing information in ones and zeros can take up a lot of space. For example, if you wanted to store a 3-minute song digitally, it would take up over 30 megabytes of space. A 1-hour HD video would take 800 gigabytes. In the real world, digital information is compressed to take up less space. A 30 megabyte song can be compressed down to 3 megabytes. An hour-long video can be compressed from 800 gigabytes down to just 1 gigabyte. Sometimes compression is lossy, which means that to save some space, some of the information is thrown away. For example, an image can be compressed to a lower resolution to lose some detail. Lossy compression is useful because in many cases, the human eye or ear can't even notice the details that are being lost. When you compress data without losing any details, that's called lossless compression. This means the compressed data can be decompressed back into the exact original. One way of doing lossless compression is to find patterns in the data you're trying to compress. As an extreme example, imagine a book about dogs with hundreds of pages using only one word. Each page just says dog, 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 over and over 1 million times. Instead of writing it all out, you could just store the pattern, dog times 1 million. Now that's a silly example, but let's look at a more real example. Instead of a book, imagine the lyrics of a song. If a single word or phrase is repeated a lot, you can store that once and then reuse it without repeating the data.
Let's see how this works with a simple text compression widget. This widget lets you experiment with compressing text. You want to represent the original text with as few bytes as possible. The widget lets you try compressing different ways and see it as it happens. Let's see how it works. The widget shows you some text to compress. In this example, lyrics to one of Aloe Black's songs. In the dictionary area, you can type patterns you see in the text. For now, let's just look for words that repeat. As you type in the dictionary area, a single symbol would be substituted in the main text area. In the example here, you can see each occurrence of the words I was has been replaced with the symbol of a sun, and I'm has been replaced with an umbrella. If you sent the compressed version of the lyrics to someone, you'd also have to send along the dictionary so that they could reconstruct the original text. So the question is the total number of bytes in the compressed text plus the bytes in the dictionary less than the number of bytes in the original text? The answer is yes for our current example, and the widget shows you how it's calculated. We assume that every character that needs to be sent takes 1 byte. So the display shows the compressed version of the lyrics with the symbols substituted in it has 216 bytes, or characters. It also shows the number of bytes in the dictionary as 10. This is to store the words I was and I'm, also the symbols that represent those patterns. This gives us a total of 226 bytes. We can see that the original text had 240 characters, or bytes, so we've reduced the bytes needed to represent the poem by 14 bytes, or 5.8%. Not a bad start. Looking for words that repeat is a good start, but you can look for other patterns. Sometimes a repeating pattern could be a subpart of a word or many words. Here's where it really gets cool. You can find patterns that include dictionary symbols you just made. For example, we replaced words I was with a sun symbol, but now you can also see that a new pattern, didn't know, sun symbol, lost. You can type this in the dictionary too. As a side note, to enter the sun symbol, you need to copy and paste it, unless your keyboard has a sun on it. With that little change, we're now up to 26% compression. Try it yourself and see if you can do better.
The repetition in a song lyric or poem is obvious, but really any form of information can have repetition or patterns in it. They're just not as obvious. For example, an outdoors photo can have a blue sky, and instead of storing every single blue pixel, that can be compressed. With the amount of information that's digitized and sent around the internet every day, there are much fancier ways to compress the data. Data compression is now built into how every picture or song or movie is stored, and almost every web page you visit is compressed as it's sent to your device. All these compression algorithms have one thing in common. They all aim to represent the information in the smallest format possible, in a way that can be decompressed to reconstruct the original, or at least something close to it.
Okay. All right. You need to navigate in your code.org to lesson 9 and go to level 2 and try to compress the text. This widget will let you use symbols to compress text in the center of your screen. You can type in the dictionary on the right side. As you do, the text on the left side will update with your symbols. You have 4 minutes, let's say around 3 minutes, to try and compress this text as best you can. So stick with this poem. We're all going to compare our numbers afterwards, and I want us working on the same thing. Does everyone know where you're supposed to be?
Wait, is it the lossy one or the lossless?
We're working on lossless compression. Lesson 9 in code.org, level 2. So if you go to, let's see, no, I don't want that.
I'm on it. It's just because it has like
No
multiple
worries.
choice questions.
Hang on. So if I go down here to lesson 9, I want to do the widget text comparison. Okay, look for patterns of repeated words. Enter the patterns as you see in the dictionary on the right. As you type entries into the dictionary, the symbol of the entry inserted will take the place in the pattern. So you're going to be typing over here in the dictionary and trying to reduce this. Make a note of your compression rate. Okay, it is 204. We're going to come back at 207. Okay, everyone's just doing this by themselves on their code.org. Let's go. Okay, well, so I'll give us till 208. Okay, let's come back and share in the chat. What are some of the compression numbers that you're coming up with? That's also going to need to go in your worksheet. Somebody start typing in the chat, what was their best compression for this so far? Wow, a 37.5. That's huge. 33, 29, 35. We have a class of overachievers, I can tell you, 27. My others were ranging more from 23 up to 35. Wow, Noah, great job. We're going to hold you out. Noah got an amazing compression. Can you tell people what are some of the techniques that you're using? What system are you using to do your compression? Noah, can you help people to understand what are you doing to compress that's getting you such good readings? Just find repeating words. Well, everybody I'm sure is trying to find repeating words, but they're not doing as well as I've never seen a 43. So you must have figured something out. Let's see, let me look in here. Ethan Z, what techniques are you using to figure this out? Ethan?
Yeah, I look for patterns in the text.
Okay, when you say patterns, what exactly are you looking for? What step-by-step strategies are you using to compress your sample text?
Repetition.
Just repetitions, anything, but what's been the most successful?
Wait, sorry, could you repeat that?
What's been most successful for you in terms of what gets you the best result? I'm driving at something. Repetitions that are large. Like you can get a whole little chunk, a phrase like pitter patter. The bigger the piece you can pull out, the better your scores are going to be. Words that repeat. Here's a weird one. Let me try. Jessica Klein. What other things other than words are you compressing to get such great numbers?
Combinations of words. So like I had I was, and then I took the symbols for I was and put in lost. So you combined parts of the sentences together. Okay.
So we're going to all go back and do this for another 2 minutes and see if everyone can get like up to a 35 or something. Getting over a 35 is hard. Think about what phrases can you pull out? What words can you pull out? And here's a crazy one. What other things are in there? There's punctuation, commas. There are spaces. All those underlines are spaces. Spaces can be saved. So, all right, it's 211. Let's go to 213. Everyone try it again. Let's see if you can beat 35. Okay. Uh, let's ask the simple question. Was everyone able to beat your numbers? Did everyone beat their best number before? Okay, great job, great job. Was anybody not able to make it to 35? I'm guessing there should be a bunch of you because I know this is tough stuff.
Me.
Okay. All that it's going to take, it's you just have to keep looking for the repetitions, for anything that you can squish down a little. That idea of nesting things, that there's things you can find in there that are repeated. I mean, vaguely, you could do the letters if it got down to it. But you understand the basics. So what we care about is down here, what our compression rate is and how much we're reducing the size of our article. Now we're gonna break into teams of ideally 2, maybe 3. And what we're gonna do is click the drop-down menu and explore other text to compress with your partners in the breakout room. Be looking for texts you predict will be easy to compress and texts you predict will be difficult. Okay, step 1, when you go into your breakout room, with your neighbor, choose an easy message and a difficult message for both of you to attempt together. Step 2, pair compressing. Use one computer, share your screen, and work together to compress the easy messages as much as you can. Now try to compress the difficult message as much as you can. See if you can best your partner. So we're just having a friendly game of one-upsmanship here, seeing how well you can do an easy and a difficult compression. So I'm going to put us in our rooms. We're going to come out at 2:19, and then we'll talk about this and see what makes for what you think is an easy one and what makes for a text that's more difficult. Okay? Pick whichever ones you think are going to be easiest and most difficult. All right, in we go. Remember, talk in your rooms. Okay, Noah, you there?
Yeah.
You should have a room to go into. I don't know who the other one is. Who else is stuck in here? Who is our starship? No, do you just not want to be in the room?
It's not letting me go on one.
Oh, no. Hang on.
It says trying to connect and it just kicks me here.
Oh, look, well, we lost our starship. Why can't I move you into, it's so weird. Well, don't worry, just try and pick out an easy and a hard one on your own.
Can you read what I sent to you?
Hang on, I've got, oh, that's really weird. Whatever, we'll make it. Okay, it's about 30 seconds till everyone's back. We can start with this. What made some messages easier to compress than others?
Repeating phrases and letters.
Yeah, you pretty much got that one. Let's wait till everyone gets back. Five, four, three, two, one. And everyone is back. So welcome from your adventure. We already were talking about what made some of the messages easier to compress than others. Does somebody else want to throw out there what they think why? You can use the chat or just unmute. Why are some messages easier to compress?
They have more repeating patterns.
Right. More repeating patterns makes it look like it's going to be easier to compress. It's a visual thing. What made some messages more difficult to compress than others? So longer messages I'm getting. What's the problem with longer messages? If the long message was the dog book, that wouldn't be a problem. Different words without any patterns. That is exactly right. You have a bunch of different words and there's not any particular pattern. That makes it difficult. Okay, how much compression were you able to get with your easiest compression?
We got to 85.94.
Up to 85. I'm betting that that was the AAAA one.
Yeah.
I've heard of 85 on that. What were you getting for the one that didn't work, that was difficult?
For our more difficult one, we got to 58.73.
Wow, that's huge for a difficult one.
Well, I would say it wasn't super difficult, but it was definitely more difficult.
Okay, but think of that range though. That like if everything was one letter, the best compression you could get is about 85%. Because if you get 100% compression, there's no message left. So most normal messages are probably going to be like in that 20 to 30% range. Okay, that's usually what you're compressing. Okay, now, so lossless compression. Lossless compression is a process for reducing the number of bits needed to represent something without losing any information. This process is reversible, 100% reversible. Lossless compression is a process for reducing the number of bits needed to represent something without losing any information. Lossless, you're not losing anything. Now we're going to go into lossy compression. So can someone sing out, what is the hallmark of lossy compression? Where in lossless, we don't lose anything. In lossy,
lose something.
We lose something. You lose some data. They are losing that data and it's never coming back. But the good news is, like in the video, typically you're doing that with big files like movies or video, music. The data that's been lost is so fine, your ear and your eye can't really tell that it's missing. Okay, so how is this widget similar to the widget we used in the lesson before? How is it different? What's happening with this widget? Can you tell? Let me go back. Can somebody give a guess about what's happening in this widget? This is the regular message up top, and this is the compressed one. What's it doing to make this compression?
It looks like it's removing some vowels, maybe like if a word has multiple vowels in it,
okay,
it gets removed.
So think of this, what we were talking about before, the idea that you're trying to make some rules that you can make your compression from. And ideally, those rules are going to be called a heuristic. And the way that having a list of steps to go through to process data is also creating an algorithm. So this widget claims you can keep, this is its rule, keep the first letter of a word and remove all vowels. Ideally, if you do that, the result will still be readable. Let's test it out. What are some other sentences we could try? We're not going to do that right now because we're very short on time for this, but you can see how keeping the first letter, which means that A gets to stay there, I gets to stay there, you can actually puzzle out the message relatively well. But the problem is you're having to puzzle. You're having to work at it. Okay, so now back into code.org. We are going to go to lesson 10, level 2. Yesterday's widget was an example, or earlier today, the widget was an example of lossless compression because you could always reverse the process to recreate the original. This widget is an example of lossy compression because some information gets lost, making this process not reversible. In today's lesson, we will investigate how lossy compression works with images. The 3 kinds of things that lossy compression typically applies to are videos, photos, and music, because those are our 3 largest file types. Why don't we use lossy compression on text? Can anyone guess? Audrey? Can you guess why we use lossless on text and lossy on big files?
They don't use it on text because you want it to be like readable still, like easy to read.
You need it readable, but it's also that text just does not have that much information in it, that you don't need to compress a whole lot of information out of text because the files are relatively small to begin with. So if it doesn't hurt that much, the idea of keeping everything is fine. Once you get into these bigger files, there's no way to create symbols for the vast amounts of data that are in there. So that's why you use lossy on big files and lossless on little files. Okay, so here's the widget. If you go in to code.org, hang on, I'm gonna go down to lesson 10, and I go into 2. Can you see this? I don't think you can. I'm gonna stop sharing and start sharing on my, okay, so this is what we've got. If you hit run, run the program by clicking the orange run button on the app. Try to use the app. After a minute, answer the following questions. You slide the slider, and that is going to compress your image. Down below here, you see what the original was. You see what the sample size is. The sample size is going to be bigger and bigger the smaller we make it. And then this is the final compressed file. So what are you seeing as you play with this compression scheme? What do you notice about the quality of the image as you compress it? You can write in the text, or you can just sing out, unmute yourself.
It gets worse.
And as it gets worse, what do you notice about the compressed file size?
It gets smaller and smaller.
It gets smaller and smaller. The smaller it is, the worse it is. And what's great about that is that it really makes sense with what we learned in black and white. When we were on black and white, what was making it so bad? It was the sample size. We were using big sample sizes. So when we use big sample size, this is the sample size is the size of these boxes. As the boxes get bigger, the image gets smaller, but it gets harder and harder to recognize. So a question is, how much compression do you need before, or what's the lowest you can compress this and still be able to recognize that as a bus? What's your feeling? Is it?
I think I'm having a problem with this. I only have access up to lesson 5 on Unit 2 Digital Information, or sorry, lesson 6. I don't have access to lesson 10 or anything.
In code.org?
In code.org.
You should have access to everything in code.org. How were you able to do the black and white pixel widget? How are you able to
I was able to do the black and white pixel widget.
The what?
I think I had the same problem. All I had to do was hit the back tick on the top left, and then it redirects me to where I'm supposed to be.
Okay.
Thank you. Thank you, team. Again, you guys can probably answer your questions better than I can because I'm not seeing what you see. So, okay. Are you where you need to be? Were you able to find this widget?
Yes, I was.
Okay. Yay, go team. Well, all I was driving at is when we start out, we have a sample size of 1 and 20,000 or 200,000 bytes. If we cut that in half, let's say we go to 10, or actually, if we cut that in half, that's 1,200, 8, I'm just seeing if I can get it to 10. Whatever. You can tell that's a bus. Let's take it down by half again to 400. That's 7 sample size. You can still pretty much see that's a bus. Once you get down to 2,000, this is 10 times smaller than the file. It becomes difficult to tell that's a bus if you had no idea. Okay, so the next one is not that great. It's basically the same thing. So this is the same bus. It's trying to let you use one of your pictures in here, that you can put a picture with a URL in, but I've never been able to make it work. So click the new image, paste in the URL, find the highest compression rate, lowest numbers possible where your image is still recognizable. That's what I was just doing with you before. This, let me see if I can go to a new page. Yeah. If you can, we can share out our compressions. I think we're going to skip this. Let me get back into screen share. All right, this is going to be better for us than writing these down. So this is in your discussion. You need to do a discussion about this in your module. So if you look in the module, okay, hang on. So in your module, down here, lossy compression. This is a discussion group that you're going to need to answer the questions to. So when we are looking at our fabulous presentation, of course, now I've lost my presentation. No. Okay, so how much is our big question? How much, when do you want to use these different kinds of compressions? So scenario 1, you're going to have to answer these on your thing, so just keep a track of which one we like best. You're sending this as a text message to a friend, but you've almost run out of data on your phone plan. Which one is going to work for you to send a text message, but you've got very little data? Again, you can write in the chat or you can just unmute and sing out. 4, Madison says 4, Julie says 4. Everybody like 4? So if you are really about to run out of data, your best choice to send a photo is to put the largest amount of compression on it you can. The problem is your friend probably can't tell what this photo is. So a thought is maybe to send the medium amount of compression, so it's as little data as possible, but they can still see it's a street scene and not something out of Minecraft. Scenario 2, you're a crime scene photographer, and this image is part of a crime scene photo. Do you want 1, no compression, 2, a small amount, 3, a medium amount, or 4, a large amount of compression? Everyone's all over this. Number 1, you want the original image because this is a crime scene photo. You want every detail you can possibly have in there. So yes, you want the original image, no compression. Scenario 3, this image is part of satellite imaging assignment for the military being used for intelligence gathering. 1, 2, 3, or 4, they're the same measures. 1 is no compression, 4 is the most compression. You're all right, everyone is on the bandwagon with 1. This is satellite military intelligence gathering. Satellite's taking a picture from space, so we do not want to degrade that when we're trying to look at things on the ground. 4, you are a social media manager, so this one's a little more questionable. Posting this to an Instagram story for an event that is happening right now. Which compression do you use? No compression, small amount, medium, or large? Okay, we don't think you need to use social media, so we got a lot of 1s and 2s. Why are you thinking that you want to be sending out an uncompressed image on social media for an event that is happening right now? Someone can unmute themselves if they want to explain. Why do you think no compression is the way to go?
You're uploading it to social media, so like the file size doesn't matter because that's on the company that's running it.
Right, but it's going to take a little longer for your stuff to get encoded and to go out, and people receiving it, they might not have that much data, those kinds of things.
Wait, is it just a picture or is it like a video?
It's a social media manager posting, no, it's our photo. It's just a photo.
Oh, so then it shouldn't take long, right?
I agree. Shouldn't be terrible. And so, but here's another weird thing to think about. You're trying to get people excited about what you're seeing or to tune into this event, right? You're trying to show them something really cool. So my thought would be that it would either be 1, the original image, or maybe a little compression. So the original image, you can hardly tell the difference. So people get that visual impact, but I'd still be making it a little quicker to get out to everyone. I think that's your worry, is if I use a full res image, is my message going to get out to everybody instantly? Or is it going to take a minute for that big a file to get compressed and then sent out? So I think we're all right on the right track, but just understand some of these are not yes or no answers. It depends on what you're trying to do. Okay, like this one. This image will be part of a collage where 100 copies will be stitched together to make a large image. Which image should you use for that? We've got some 3s, some 2s. Does someone want to explain why they're thinking that 3 is the way to go here? A medium amount of compression.
A medium amount is fine because nobody's going to be looking at the specifics of this one image.
Right. To me, it's really a question of, does the image work better for your thing? That each one of these looks a little different. And if I'm making an image out of 100 of them, I might want to use them all. I think what they're trying to get at is if I use 100 high-res images, this final image is going to be really big. But it doesn't really define what you're doing with it. Are we printing these and pasting them on a board all it's saying is it's going to be a part of a collage, not a digital collage. So I don't think it really matters which one. It's which one looks right for your place in the collage. But that's it. Oh, here, we're professional photographers submitting a design competition. I think you all know which one you would choose. Carefully judge for color and composition. Of course, we would go with number 1. Okay, so what you're going to take away from today is, when is it a good idea to use lossless compression versus lossy? Can someone unmute themselves and tell me, when is it a good idea to use lossless compression?
Lossless compression is good when you're trying to like send a message or like something very specific with words.
Absolutely. Lossless, again, lossless seems to be associated primarily with text. Creating, written messages and being able to compress them down smaller. When would you use lossy compression?
Videos and images.
Big files. Okay. And remember, when you're being asked questions, like with those series, what are the important factors in making that decision? Some of them are going to be human factors. Do you think this is appropriate? Maybe yes, maybe no. So some of this is just your judgment, but it's the basic idea. If it's a really big file, you want to shrink it down. You're going to lose some data. If it's a text message, we can make that work. I think class is over, so let's end with our lossy compression definition. Lossy compression is a process for reducing the number of bits needed to represent something in which some information is lost or thrown away. The process is not reversible. Okay. A process for reducing the number of bits needed to represent something in which some information is lost or thrown away. That is a lossy compression. The process is not reversible. All right. Well, great day, guys. We have definitely made it as far as anyone. Any questions? You can go now. You can hang out if you have a question.
Mr.
Thank
Swift?
you.
Can we
Yay!
the graded
Thank you.
discussion?
Thank
Yeah,
you.
you need to
Thank
turn
you.
in your work